So the final reaction, or the final experiment for the lab class, is a Grignard reaction. So you covered that pretty early on in lecture, relatively speaking, but we put it off to the last reaction because it's kind of the most complicated in terms of techniques. So the intended reaction for you to carry out would have been to start with bromobenzene, and you would have dripped it into a mixture containing magnesium and ether. Usually we kind of scrape the magnesium clean so that it is as reactive as possible, and then that allows us to get the magnesium to insert into the carbon-bromine bond in order to generate our Grignard reagent. So remember, the Grignard reagent is moisture sensitive, it's a little bit oxygen sensitive, so it's not something that I can generally isolate, and the ether that we use for our reaction needs to be dry, and by dry we mean water-free. So usually we'd open a brand new bottle of the ether to start the experiment. The reaction that we intended to do was to quench the Grignard using dry ice. And generally what we do is we monitor the disappearance of the magnesium for about an hour. Hopefully it all disappears, but however much of it we started with, we want to see some of it goes away because that'll ensure that we form some Grignard reagent. So when you think about carbon dioxide, right, that's what CO2 looks like. So it's more or less going to behave like a ketone or an aldehyde. We're going to have a single attack by the Grignard, and what we should end up with as a result of that is the carboxylate. And in the lab, in practicality, we would have stopped at that point, basically left the Grignard in the dry ice to react until all of the dry ice disappeared, whether it went through the reaction or evaporated, or sublimed, I guess I should say. And then the following lab period, we would have stirred the resulting mixture with 1 molar hydrochloric acid to acidify, and then that would allow us to get the product to form. And just like a lot of times after acidification to reprotonate, we would collect the product by vacuum filtration. All right, so that's what the intent of the experiment was meant to be. I don't think I actually asked you any questions about the actual experiment. I just made it into a worksheet about Grignard reagents. So I just want to quickly go over what happens in Grignard on an aldehyde, a ketone, an ester, an epoxide, and a carbonate. So just a few quick examples of each of those. And remember, we're really not interested in drawing any sort of mechanism here. We just think of the carbon attached to the magnesium as being negatively charged. So let's say that I had this 3-carbon aldehyde, and I attacked it with this Grignard. And then, of course, we need to extend that arrow. Need to work it up by adding acid to make the magnesium go away and potentially reprotonate anything if we need to. So let's number our carbons here. 1, 2, 3. And then off of the Grignard, we'll call it 4, 5, 6. So I should end up accomplishing 2 things, right? Making a new carbon-carbon bond between carbon 3 and carbon 6, and also reducing the aldehyde down to the alcohol. So the product we should get would be that product. And if I want to transfer over my numbers, 1, 2, 3, the new bond between 3 and 6, the carbon that was attached to the magnesium, and then that's the product that we would end up with. And technically carbon 3 would be a chiral center. We don't have any control of making one enantiomer versus the other, so we should expect to get the racemic mixture from that one. So what we saw here was aldehyde getting converted into secondary alcohol. Let's change our aldehyde to a ketone. I guess I'll use ethyl Grignard. And if we're numbering again, 1, 2, 3, 4, 5, 6, at least we know our product's going to end up with 6 total carbons. Same idea in general here, right? That I'm going to make a new carbon-carbon bond, this time between carbon 3 and carbon 6, and turn the ketone into, in this case, the tertiary alcohol. So there's a lot of ways to draw this, but I'm just going to show the Grignard reagent adding on, not along the chain, but above the chain. That's at least the way I'm imagining it happen. So the new bond we formed is there. This makes it 1, 2, 3, 4, 6, 5, like that. And what we observed here was the ketone getting converted into the tertiary alcohol, right? The carbon bearing the OH, carbon 3 in this case, is attached to 2 other carbons. That makes it tertiary. And in the previous example, the carbon bearing the OH was attached to 2 other carbons, so that makes it secondary. If we have an ester, then really the way to think about what would happen with an ester, I'll just use ethyl Grignard again, that's fine, is we're really going to end up with a double attack. So the ester will get converted into the ketone after one attack, and then the ketone will go through a second attack to make a tertiary alcohol. So 1, 2, 3, 4, 5. So then let's do this in steps, right? The first attack is an addition elimination, so the O-methyl group goes away, and then I would add those 2 carbons. So if I'm numbering here, it's 1, 2, 3, I guess 5, 4. And then we can't stop the attack of an ester at 1 addition, because now we've got a reactive Grignard and something that we know it would react with in a ketone. So it'll happen again, and again the ketone will turn into a tertiary alcohol. I guess I didn't write this before, right? The previous example happens to be a chiral. This product also happens to be a chiral because the side chains are all the same off of the tertiary alcohol. We can also talk about what happens with a carbonate. So with a carbonate, our reactive intermediate would be something like this. That's called diethyl carbonate. And think about it like it's a double ester, right? So what I'm expecting here, oops, let me fix that. What I'm expecting here is rather than a double attack, it'll be a triple attack. So 1, 2, 3, Grignard, and then 2 H3O plus. So from the initial reactant, the only carbon that I'm going to preserve is the carbon that's at the center. The other 2 chains are going to be lost by addition elimination. I can number my Grignard 2, 3, 4. And so let's show the result of each of these attacks. And same story here like with the ester. I can't stop it after 1 attack. It's going to keep happening. So first I'll replace the right-hand side O-ethyl group with my 3 carbon Grignard. 1, 2, 3. So if I'm numbering, it's 1, 4, 3, 2. And then again, we can't stop it with the ester, so it's going to now replace again. So then that would be the ketone we end up with, and even with my weird numbering here, right, 1, 4, 3, 2, and then again 4, 3, 2. And then we know that from the ketone, it will happen again. So notice we triple attack, which is going to guarantee that we end up with a symmetric tertiary alcohol. So then let me mark the new bond in each case. So in the first intermediate, 1 and 4 got attached. Then on the left side, 1 and 4 got attached. And then kind of coming off of the chain, 1 and 4 got attached. Okay, the last example is what happens with an epoxide. So with an epoxide, it's going to go through a single attack. Use a 2-carbon Grignard, then H3O plus, work up. So if I number my epoxide 1, 2, and my Grignard 3, 4, what's going to happen when the epoxide gets attacked, let's say it gets attacked at carbon 2, then that's going to break the carbon-oxygen bond. So what's going to make the result of the epoxide reaction different is that the new carbon-carbon bond isn't occurring with the carbon that used to have or that still has an oxygen attached. The oxygen's getting transferred over. So when we look at what's going to happen here, here's carbon 1, then 2, 3, 4, like that. So carbon 1 retains that oxygen, right? All I broke was the bond between carbon 2 and the oxygen. So let me draw a dotted line here. That used to be the bond connection, but that's what broke in the Grignard. So the other Grignard reactions are really showing that we're reducing from one state to another. The epoxide's different in that regard because we're just breaking that CO bond. And then the other thing to say for an epoxide is if we have an asymmetric epoxide like this, let me number again, carbon 1, carbon 2, then an epoxide is going to selectively, whoops, let me draw that in black, is going to selectively be attacked at the less substituted carbon. So that's an important thing to think about as well. So now we'd expect that attack from my Grignard will happen at carbon 2 and then break the carbon 2 oxygen bond. So how's that going to look? Well, here's my OH, carbon 1, which has these 2 branches coming off of it, carbon 2, and then 4, 3. Let me number here. 3, 4. So then in this case it's 1, 2, 4, 3, where the new bond is made between carbon 2 and carbon 4. All right, so that's a pretty quick recap on what's happening with Grignard reagents for the standard reactants, aldehyde, ketone, ester, carbonate, epoxide. And you also saw what was going to happen in this actual experiment where we're going to use dry ice, CO2, as the electrophile in the reaction. And remember, for that, we only get a single attack. All right, so yeah, hopefully you should be able to answer everything in that experiment 9 handout now.